All right. Hey, everyone. This is Miss Turk. I'm here to talk about the 5.5.3 test at the end of Unit 5. All right. So I'm just going to give you some hints, and I'm going to omit one of the questions as well. All right. So what is the most likely oxidation state of chlorine? So the most likely oxidation state is what we see at the bottom of each group on the periodic table. It's the charge that that atom is most likely to have when it forms a bond. Okay. For part B, identify the oxidation state of chlorine in the following compounds. So for this, you need to click on that FYI in 5.5.1 on page 5, which is the rules for figuring out the oxidation state. One of the rules is that any element alone, its charge is 0. Even if it's bonded to itself, it's considered alone. Okay, so alone, like by itself, or bonded to itself, the charge is 0. Okay. So I know that you see this and you're like, chlorine, okay, chlorine's charge is 1 minus. That's its most common oxidation state, but it can have other oxidation states as well. This is the most common oxidation state when it forms a bond, but when it's alone, its charge is 0. When it's bonded to itself, its oxidation state is 0. So this one would be an example where it was 0. So anytime you see an element alone, like Mg, or K, or Na, or Ag, or any element bonded to itself like O2 or Cl2 or Br2, the oxidation state is 0. Okay. Now when the element bonds to a different element, that's when it has an oxidation state that's positive or negative. It's no longer going to be 0 once it bonds to a different element. Okay. The most common oxidation states are the ones you see here. So when these bond to another element, they're most commonly 1 plus. Or, when these elements bond to another element, they're most commonly 2 minus. But there's other possibilities as well, okay? So what you need to do is look at the overall charge of the whole compound and then kind of work backwards from there. So HCl, notice there's no charge. Overall, these charges add up to 0, okay? Well, if you look at the rules, you'll see that H is always going to be 1 plus. Plus H is, and it's in the column for 1 plus. So if the H is 1 plus and everything adds up to 0, the Cl must be 1 minus, okay? And luckily, that's the most common oxidation state of Cl is 1 minus. So in this case, the chlorine is 1 minus. This next one is not a compound, it's a polyatomic ion, which is essentially a molecule with a charge, okay? Like this is a molecule of HCl that had a charge of 0. This is a molecule of ClO3 that has a charge of 1 negative. So all these oxidation states need to add up to 1 negative, okay? And if you look at this list, it says always assume chlorine and oxygen can both have multiple oxidation states, so it's very hard to tell. But oxygen, if you see an oxygen though, you can assume, let me correct what I said. Chlorine can have multiple oxidation states. Usually it's 1 minus, but it can also be 7 plus, 5 plus, 3 plus, or 1 plus. So that's a lot to choose from. Oxygen, on the other hand, is always 2 minus. Okay, so that's one of the rules to go by. As soon as you see oxygen, make it 2 minus. And there's 3 of them. Okay, so if we have 3 oxygens, 2 minus, 2 minus, and 2 minus, that adds up to 6 minus, okay, or negative 6. We need the overall charge of this whole molecule to be 1 negative, though. Okay, so if we have 6 negatives, the chlorine must be 5 positive, and 6 negative and 5 positive makes an overall charge of 1 negative. Okay, so in this case, the chlorine is 5 positive. So you have to work backwards a little bit there. Okay, redox reactions. So to determine the oxidation states, look at 5.1.1, page 6. Remember, any element by itself is 0. Okay. Barium, Ba is in group 2. It's going to be 2 plus. Z when it's in a bond, but when it's alone, it's going to be 0. Zn, if you look on the back of the chart I gave you, zinc is always 2 plus. Okay. You can't tell from its position here because there's nothing down there. But remember, these ones are on the oxidation states are on the back. So zinc is always 2 plus when it forms a bond. When it's alone, it's 0, but when it forms a bond, it's 2 plus. And like I said, the oxygens, just assume they are all 2 minus, okay? So we got to do a little working backwards to figure out the sulfur. So like I said, the zinc is 2 plus. We have 4 oxygens, each with a charge of 2 minus. So 2 minus times 4 is 8 minus. So if this is 2 plus, this is 8 minus. The sulfur, if this all adds up to 0, this all needs to add up to 0. The sulfur is 6 plus. Okay. And then over here, we can see the zinc is now alone. So now the zinc is 0. The barium, which was 0, is now 2 plus. We have 4 oxygens again that are each 2 minus for a total of 8 minus. So the sulfur must be 6 plus. Okay. So you can go ahead and figure out reactant is before the arrow, and then product is after the arrow. So you can go ahead and fill those in for the zinc and the barium and the sulfur and the oxygen. To explain why this is a redox reaction, you can look at 5.1.1, page 6. To write the half reactions, you can look at 5.1.3, page 4. These you are only going to find the element that was oxidized and the element that was reduced. Those will be the only thing in the 2 equations. The element that was oxidized, and include the electrons, whether they were gained or lost. And then the element that was reduced, again, include the electrons that were gained or lost. But the elements that were not oxidized or reduced, they're not going to be in the answer to B. If you're not sure on the definition of oxidized and reduced, you can look back at 5.1.4, page 14. You'll be able to figure out which one was which. And then in part D, this term oxidizing agent and reducing agent, this is kind of old-fashioned. They even removed this from AP chemistry. The thing that was reduced was the oxidizing agent because it caused the other thing to oxidize. And the thing that was oxidized was the reducing agent because it caused the other thing to reduce. Okay, so that's kind of how you'll kind of flip-flop your answers from C for part D. All right, then we have an example of an electrochemical reaction going on. Here's the equation. Just read this to yourself. What makes this an oxidation reduction reaction? You can look back at 5.1.1, page 6. Write the half reactions, okay? So you're going to have to figure out what was oxidized, which one had a charge that went up, which one had a charge that went down. And then one of the elements, the charge didn't change, okay? And that's not going to be included in B. So your 2 half reactions, you'll have a half reaction for the element that was oxidized and a half reaction for the element that was reduced. You can look at 5.1.3, page 4. And then they're asking what was oxidized and what was reduced, meaning which element. Okay, so again, you can look at 5.1.1, page 14 if you're still not sure. And then in this simple electrochemical cell, what functions as the anode and what functions as the cathode? So look at 5.2.1, page 8 for the definition of anode and cathode. And then you can figure out which element was at the anode and the cathode. And for part E, is this a galvanic cell or electrolytic cell? It's galvanic cell because the reaction, I'll just tell you, the reaction happened without an input of energy. The reaction just happened spontaneously. She didn't need to plug it into anything to get it to happen. So that's how you know it was a galvanic cell, is that it just happened on its own. F, you can just omit that. You don't have to calculate the potential. For part A, we're going to write half reactions again. So I'm going to help you with this one just because we haven't seen it written this way before. So you have Mg turning into Mg2 plus, and then you have Au1 plus turning into Au. Okay, so you can see that Mg went up, its charge went up. When the charge goes up, it's oxidized. When the charge goes down, it's reduced. And remember, oil rig was in your reading. Oxidation is losing electrons. Reduction is gaining electrons. Okay, so this is oxidized. It's losing electrons. It's giving off electrons. So 2 electrons are going to come off of this atom when it turns into Mg2 plus. Okay, so it started out as a neutral atom. It lost 2 negative electrons that it gave away. And the Mg then became an Mg2 plus ion when it lost those electrons. The gold, on the other hand, was reduced. Reduction is gaining electrons, Rig. It's going from 1 plus down to 0, so it just needs to gain 1 electron. Okay, so a positive ion with one negative electron, gaining one negative electron makes a neutral Au atom. Multiply each half reaction by the correct number in order to balance the charges for the two half reactions. So what you need to do is, because this lost 2 electrons, but this gained 1 electron, we need to even those out. We've got to multiply this whole thing by 2, okay? So we're going to make it 2 Au, takes 2 electrons to make 2 Au, 1 positive ions, gains 2 electrons to make 2 Au atoms. Okay, so you can see how it's kind of balancing out. It's taking these 2 electrons from the Mg and they're being incorporated into the Au. Okay, so that's what they mean by that part. So you can just write that for part B. And then for our part C, add the equations and simplify to get a balanced equation. So what they mean is just add these two together. So I'm going to bring the arrow down. The 2 electrons cancel out, okay, because they're before the arrow and after the arrow. So just write down what we have left. Mg plus 2 Au positive yields 2 Au plus Mg 2 positive, like that. So that's what you would write down for part C. And that's it. Okay. Question 5, stoichiometry, my favorite. Okay, so part A, what is the mole ratio? What is the ratio of moles of AlNO3 to moles of Na2CO3? So there you just look at the coefficients, okay? Moles is a unit it's a numerical unit, okay? So for every 2 moles of this, you need 3 moles of this. Just like for every 2 dozen of these, you need 3 dozen of these. A moles is like a dozen. It's just more things, okay? So it's a 2 to 3 ratio. Now in part B, it's a big calculation. So I tried to kind of set it up for you because I know that this is a lot. It's saying if you react that much AlNO3 with that much Na2CO3, which would be the limiting reagent. I'm teaching it in a slightly different way from the way the book did that I think is easier, okay? The limiting reagent is the reactant that gets used up first. We can't really tell by looking which one's going to get used up first. You can't just say, well, there's more of the AlNO3, so I bet the Na2CO3 will be used up first because there's less grams of it, okay? But that doesn't take into account, like, each formula unit of Na2CO3 doesn't have the CO3 doesn't have the same mass as each formula unit of aluminum nitrate. Mass doesn't correspond to number of particles because these particles have different masses. So it's a very complicated thing that you can't just figure out in your head. You have to do a calculation. So start with each reactant and then convert it to moles using the molar mass. The molar mass is the grams in 1 mole. It's the grams in 1 mole. So you can put 1 where moles is. Okay, to find the molar mass, you just take your periodic table. Okay, and what we used to call the atomic mass, we learned is also the molar mass. Okay, so this number down here, it's the AMU in 1 atom, but it's also the grams in 1 mole of atoms. Okay, so add up the mass of an aluminum. And then it's bonded to, this should be a 3, not a 2. Oops, that was my mistake. It's AlNO3, 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 AlNO3. That was my mistake. So what you need to do is add up the mass of an aluminum, and then we have 3 NO3s, so distribute the 3. So an aluminum plus 3 nitrogens plus 9 oxygens. And that's what will go here. That's the molar mass of aluminum nitrate, okay? And then for this one, to add up the molar mass of sodium carbonate, you add up the mass of 2 NAs. So you'll do 2 times this, 22.99, plus the mass of carbon, 12.01, plus the mass of 3 oxygens, so 3 times 16, to get the molar mass of sodium carbonate. So the molar mass is the grams in 1 mole. So the molar mass goes next to grams and 1 goes with moles. Okay. And then for this next part is when you're moving from the reactant to the product that we're asking about, okay? This only has 1 product. So this is what you're going to go to. If there were multiple products, just look ahead and see what they're asking you about in the end. You can see in the end they're asking how many grams of Al2CO3 should precipitate out of the reaction. So we know that's where we're going. because they're asking about it later, but you can tell that's the only product to go to. So that's why I went to Al2CO33, Al2CO33. So whenever you see moles over moles, that's the mole ratio. How many of these for every how many of these? How many of these for every however many of these? That's when you look at the coefficients like you did in part A. So the coefficient of Al2CO33, there's nothing in front of it, so its coefficient is a 1. And then AlNO33 has a coefficient of 2. Okay, look at the number in front. So it's for every one of these, you need 2 of these. Does that make sense? It's a numerical ratio. For every one of these that's produced, you need to start with 2 of these. For this one, the Al2CO33, once again, is 1. For every one of these, however, you need 3 Na2CO3s. It's a 1-to-3 ratio. Okay, so those are our mole ratios. And then at the very end, we are converting from moles of the product to grams of the product. So just like here, we went from grams to moles of reactant. Now we're going from moles to grams of product. Okay, so take the Al2CO33, so you're going to add up the mass of 2 aluminums, 3 carbons, and 9 oxygens. It's going to be a pretty big mass because that's a pretty big particle. And that's the grams in 1 mole. So once again, the 1 goes where moles is on the bottom. And whatever you got is the grams. Because we're going to the same product both times, you're going to put the same molar mass both times. It's the molar mass of Al2CO33. I couldn't quite fit that in with the units. Okay? So you're going to the same thing. And essentially what you're figuring out is, if I used up all of this reactant, how much product would I get? And if I used up all of this reactant, how much product would I get? Okay? And in truth, we're not going to use up both reactants. You're always going to have one that has a little bit of leftovers or a lot of leftovers. So go to the product, and whichever reactant leads to less product, that's the limiting reactant. Okay, so it says what would be the limiting reagent? That's the limiting reactant. So look at your answers. Whichever led to a lower answer is your limiting reactant. Again, limiting reactants are not numbers, they're things. So it's either going to be AlNO33 or Na2CO3. Okay, so just write down the one that led to less product. That's the limiting reactant. Okay, and put a big X over the calculation that led to more product. That can't happen. Okay, the limiting reactant is what determines the amount of product. The excess reactant won't be used up, so we can't use that to predict the product. So we killed 2 birds with 1 stone. Okay, so we figured out the limiting reagent or the limiting reactant. And then for part C, use the limiting reagent to determine how many grams of Al2CO33 should precipitate out in the reaction. That just means how much should be produced, okay? So whichever answer was lower, whichever grams of Al2CO33 was lower, that's how much we're going to get, okay? Because that's how much we would get when the limiting reactant's totally used up. So whatever you got there, whatever was the lower answer from part B, that's your answer to part C. All right, so part C is what we call your theoretical yield. Theoretical means it's theoretically how much you should produce in the lab if everything goes according to plan. So based on our reactant amounts, we should theoretically get that amount of product, whatever you said for C. Okay, yield means like how much you produce. However, let's say you only made 341.63 grams of that product, okay? Because things happen in the lab. There's like impurities, side reactions, things don't go as planned. So a lot of times you don't get your theoretical yield in the lab. You get less than that. Sometimes you get more than that if there's some like impurities mixed in. So this is what we call your actual yield. Actual yield is not something you calculate. It's something they will tell you in the problem, or when you do a reaction in the lab, it's how much you'll actually make in the lab. Okay, you want these to be close together, but it doesn't always go that way. Okay, so they want you to calculate your percent yield. So your percent yield is your actual yield over your theoretical yield times 100. And then you just put the percent sign after your answer. Your goal is for it to be close to 100, but a lot of times it's like 90%, 60%, even some bad situations like 30%. The goal is for it to be high, but it's not always that high. All right, and then question 6 is easy. I'm not going to go over that. That one's pretty simple. All right, so hopefully that's helpful. That is the 5.5.3 test.